I'll be presenting our work on MixApart, a way to enable MapReduce style analytics on enterprise storage systems. And the ideas for this work originated a couple of summers ago while I was interning at NetApp in their advanced technology group. I then went back to University of Toronto and continued the work, graduated, and now I'm back in the advanced technology group with NetApp, so coming full circle. So the work is a collaboration with my buddy Gokul, who's sitting in the front row, and my advisor from University of Toronto, Cristiana Amza. So I'll start by presenting the problem space. So companies today rely on enterprise storage systems, such as network-attached storage, for their data management needs when it comes to critical data. Why? Because these boxes, such as the NetApp filers, give you enterprise-level data management, right? So they have very rich capabilities in terms of data management, both in terms of data protection as well as storage efficiency. So in our recent years, we've seen the emergence of frameworks for distributed analytics, right? The Apache Hadoop ecosystem being a great example in this space. So users now have access to tools such as Pig or Hive that raise the abstraction level. So it's very easy to run computation jobs, sort of to enable these large-scale computations. So now it would be nice if we could use Hadoop to essentially analyze data that's being stored currently in enterprise storage systems and extract some value out of that data, right? So the question we're trying to ask is, how do we marry the two? How do we marry Hadoop and enterprise storage? How do we run Hadoop-style analytics for data that's being stored in enterprise storage systems? And the current approach today is to look at it in a sort of isolation. So we have the enterprise storage system that's storing the critical data. And when enabling Hadoop, companies today deploy a dedicated infrastructure, dedicated compute, dedicated storage to sort of for the needs of the Hadoop distributed file system in this case, right? So we have what we call a two-storage silo problem, right? We have two storage systems, the enterprise storage system and the HDFS, both are reliable. So one problem with this setup is the hardware costs, right? The hardware cost to provision two storage systems. A second sort of problem comes from the interaction between the two systems and sort of the data migration processes. So to enable analytics on data that's in enterprise storage, we first need to ingest the data, right? We have these periodic data ingest phases where we can rely on tools such as Flume or Scoop to transfer data from the enterprise storage system into the Hadoop distributed file system, right? So periodic data ingest is a manual process, a static process. Someone has to manage it. It's typically cumbersome. And the second problem is that all of a sudden you have data stored in multiple places, right? Data stored in multiple silos. And you have to address, for instance, data consistency issues. But the fundamental problem is this cross-silo data management, which is typically very expensive and error-prone. With our system, MixApart, we're trying to run MapReduce style analytics for data in enterprise storage systems, so off of NFS as an example. So in our environment, the enterprise storage system is the single reliable data store, right? So we go away with, there's no more HDFS, right? For scalability purposes, we still rely on the local server storage, the local disks. So we create this scale-out cache, very large scale-out cache. So in essence, replacing HDFS with a stateless scale-out version. But the main point is that instead of implementing static periodic ingest processes, our ingest happens transparently and on demand as computations enter the system. So what's the flow in MixApart? So we have the normal compute flow. We have the map phase. That is common in MapReduce. So in the map phase, there's the processing going on with data being read from the storage system. In our case, the storage system is a cache plus enterprise storage architecture. The map processes emit some intermediate data that is being sent to the reduce phase. So we have a number of reduce processes doing some form of aggregation with the final results stored back in our storage system, in the cache plus enterprise storage. For the output path, for the results of computations, those can be lazily propagated back to the enterprise storage. So we don't consider that to be on the critical path. But instead, the map phase, that is on the critical path. So that's doing synchronous I/O from the cache plus enterprise storage architecture. So some I/Os are going to come from the cache because of data reuse. Some I/Os are going to come from enterprise storage when the data is not in the cache. So they will come indirectly through the cache to the enterprise storage system. In terms of scalability, we need to understand the sort of the parallelism that such an architecture, the cache plus enterprise storage architecture, can provide to the map phase, right, to the MapReduce style analytics. And there are three factors that impact the map task parallelism, right? So first, we have the storage bandwidth. How much bandwidth can you get from the enterprise storage system? Second, there's the cache reuse. To what degree can we utilize the cache effectively? And third, it's the nature of the map input phase. How CPU intensive is that phase, right? And we use the map task I/O rates as a measure to depict that, right? So at which rate is each individual map task processing the data, at which I/O rate? So to better understand sort of the feasibility of such a design, we went ahead and we did a workload analysis. So we did an extrapolation from recent studies, and we derived three critical insights for our design. So first, there is indeed high data reuse in MapReduce workloads, right? So with an optimal cache replacement policy, you can get at around 60% hit rates in your cache. In our case, because we have a very large, on this cache, this should be achieved easily. A second insight is that the input phases are actually on the CPU side. So the I/O rates are rather low. The reported numbers on average 25 megabits per second per task, per map task. A third insight, which I'm going to cover in a couple of slides, is MapReduce I/O demands are highly predictable. So MapReduce workloads I/O demands are highly predictable. So we then went ahead armed with these numbers and we did a back of the envelope calculation, right? For what are the compute scale estimates that we can sustain by this cache plus enterprise storage architecture. And I'm plotting here the compute scale estimates in number of parallel map tasks on the y-axis and for various data reuse ratio on the x-axis. That is, what's the overlap in my workload, right? To what degree I'm utilizing the cache. And I'm showing this for a enterprise storage bandwidth of 10 gigabits per second and a map task I/O rate on average of 25 megabits per second. So to give you a better feel for what these numbers mean is, if there's no reuse in my trace, so there's no overlap across the jobs in the system, I'm not utilizing the cache as well at all, then the number of parallel map tasks that I can sustain by such a cache plus enterprise storage architecture is 400, right? Solely from the enterprise storage system. So that's 10 over 25. Now, if I do have some reuse, then I'm able to get some bandwidth, some throughput. I'm able to get some throughput from the cache. So with a 0.8 reuse, I can sustain thousands of parallel tasks. So in this case, 2,000. Right? Now, to put it in perspective, an average Hadoop cluster these days is in the order of hundreds of cores. So this is very encouraging, right? All right, so far we've covered the analysis, right? Sort of give us some motivation for continuing with the work. We then went ahead to understand what are the sort of design points to build a system such as MixApart. So first, we need a way to manage the storage backend bandwidth, right? So we need a way to, and I'm going to give you a better feel later, we need a way to saturate the bandwidth because that bandwidth is fixed with as many as possible parallel map I/O streams without impacting the job performance, right? So we could fit 1 million streams, but it makes no sense because every stream is going to be every map task is going to progress very slowly, right? So we're going to impact performance. So we need to find that point where we saturate the bandwidth while not impacting the job performance. Second, because we have a cache, we need to manage the cache efficiently, right? So we need to ensure high data reuse. And third, we need to have a way to assign computation to nodes that store cache data. So remember the predictability of I/O demands insight. This is the insight that we actually use to drive our architecture. So this is a MapReduce specific architecture that I'm going to talk about. It turns out whenever a MapReduce job is being submitted to the system, we know the input path information, so we know the files that the job is going to process. And we also know the map task I/O rates. That is, we know how the input phase is going to go through the data, the rates at which the input phase is going to go through the data. And this is because first, it seems there is high homogeneity across the jobs within a Hadoop cluster. That is, there is only a limited number of job classes within a Hadoop cluster. And second, which is more importantly, within a job, the tasks, the map tasks, are highly homogeneous. They access data at about the same rate. So even if I cannot decipher the job type, I can easily derive the map task I/O rate by getting feedback from the first task that's running. Right? Just let it run a bit and then get the feedback, and I know the I/O demands for the entire remaining job. What this means to us is that we're able to enable this just-in-time parallel data prefetching of data from the enterprise storage system into the cache. So we're able to do this within a job. So for a single job, as soon as the job is being submitted to the system, we know what the job needs are. But we're also able to do this across jobs, right? If we have multiple jobs scheduled, we can look ahead and prefetch ahead. So we use this insight to sort of drive our architecture. So we have our enterprise storage system, our single reliable data store, and the first sort of layer is the caching layer. Right, so I'm showing here the caching layer in more detail. I have a couple of cache nodes with the local disks acting as a cache. There's a manager which mimics the HDFS, the Hadoop file system name node. It's the master that sort of manages the entire distributed cache. And there's a location map at the name node level, right, for storing location information of data blocks within the cache. Logically decoupled from this cache, there's the compute layer. Right? So the compute layer, I'm showing a couple of compute nodes. There's a job tracker which mimics the Hadoop job tracker, which is a manager that manages the entire computation tier, the distributed computation tier. And while they're decoupled, the interesting point is that we make them sort of collaborate fairly heavily. Right? So for instance, because the predictable I/O demands are available at the compute layer, we need to propagate them to the cache layer. So the compute layer, when jobs come into the system, the compute layer sends that information, in this case job priorities, job order, job execution order, and job I/O demands, they're sent to the name node. Right? So in turn, this information is actually used by a component at the cache layer. We call it the data transfer scheduler. But the goal of this component is to schedule prefetches of data according to job I/O demands and job order, job priorities, right? So there are three sort of factors that the data transfer scheduler uses when deciding what to prefetch next. First is understanding what's available in terms of storage bandwidth. So if there's nothing available, there's no more room to prefetch. Second, the job priorities. So the job priorities dictate the prefetching order. And third, the map I/O rates. So the idea is to, at any given time, the enterprise storage bandwidth is going to be saturated by a large number of parallel streams that go in parallel at specific map rates. And this is the job of the data transfer scheduler to implement that logic. So it's instructing the cache nodes to do those respective prefetches. Now, remember I said that the two layers collaborate, right? So far it's been one way, but the name node actually exchanges the data location information with the job tracker, both for data that's currently in the cache as well as for in-progress prefetches. And the job tracker, there's a compute scheduler component situated at the job tracker level, which uses this location information to collocate compute and data. So it uses the location information and the job priorities to collocate computation and data. So I've talked about the architecture. I'm going to present next an example, right? So I call it MixApart in action. what happens when a job is submitted to the system, right, step by step. So I'm showing here the architecture with 4 files stored in the enterprise storage system, F1 to F4. 2 of those files are cached in XDFS, F1 and F3. A job is submitted to the system with files F1 to F4 being processed. And as soon as the job is being submitted to the system, the job tracker and the name node exchange job level information, right? The input information, IO rates, data allocation information being sent from the cache to the compute. So next, what happens is the data transfer scheduler starts issuing prefetches for the data that is not in the cache, right? So in this case, it first sends the location information of F1 and F3 to the compute layer, and second, it asks the 2 cache nodes to transfer F2 and F4, right? At the same time, the compute scheduler creates 4 tasks for the respective job, 1 for each file. And while the prefetches for F2 and F4 happen, the computation for T2 and T3 takes place. T1 and T3 takes place, right? So the computation for T1 and T3 happens on data that's already in the cache, and in the background, the prefetches for F2 and F4 take place. While after T1 and T3 finish, then the compute scheduler assigns T2 and T4 to the 2 computation nodes, as expected. So I've covered the MixApart design and architecture. Now I'm going to talk about the prototype, and then I'm going to go into the evaluation. So we try to reuse as much of the Hadoop code base as possible. So MixApart currently is a re-engineered version of the Hadoop MapReduce and the HDFS layers. The XDFS cache, our caching layer, is a version of HDFS where we disregard the reliability aspects. We did some code changes to have that in place. And HDFS, our stateless HDFS version, has NFS support for speaking with an NFS backend. The compute scheduler, the component in charge of assigning computation to nodes, implements a first in, first out scheduling policy and is cache content aware to do the collocation of compute and data. The data transfer scheduler, the component in charge of issuing prefetches based on job level information, is a new module at the name node level, just because it's specific to our cache plus enterprise storage architecture. So we did our evaluation of MixApart on Amazon's Elastic Compute Cloud at scale. We evaluated MixApart against various flavors of Hadoop, which I'm going to talk about in a couple of slides. The test bed was a 100-core compute cluster. So we deployed 50 virtual machines, 50 EC2 virtual machine instances. Each virtual machine instance has 2 cores, about 8 gigs of RAM, and about 1 terabyte of local disk space. So that's a large cache that you can build from these 50 virtual machines. So we do use the local virtual machine instance storage as cache for XDFS, as well as sort of storage medium for HDFS in Hadoop. As enterprise storage, we deploy a virtual machine on Amazon. So it's an EC2 instance that provides a total of 1 gigabit per second bandwidth to analytics. So that's the total. So we first micro-benchmarked our system. So we took this data set, 12 days of Wikipedia statistics, and as workload, we wrote a fairly simple MapReduce job that mimics a grep job, which is fairly common when benchmarking Hadoop architectures. And the job aggregates page views for a given regular expression. And we ran the job on both uncompressed input, and that's on the IO intensive side, as well as compressed input. And because decompression happens on the critical path, that's more CPU intensive. That job is more CPU intensive. So using the MicroBenchmark, we first measured the impact of data ingest in Hadoop. So remember, with Hadoop, with the current approach, we had to transfer the data from NFS, from the network attached storage into HDFS, then do the analysis, right? So I'm going to be plotting here the job durations in seconds on the y-axis for both the IO intensive and the CPU intensive jobs. So uncompressed and compressed inputs for both MixApart with no data in the cache, so it's a MixApart with a cold cache. All the traffic comes from enterprise storage, benchmarked against Hadoop, where we consider ingest. Right? So to give you an example, for the IO-intensive job, I'm showing the numbers for MixApart and Hadoop. And you can see that MixApart is faster. Right? So I'm breaking down the time for Hadoop into the time spent ingesting, doing the static ingest, and the time spent on computation. Right? And the reason MixApart is faster is because of the overlap on compute and ingest. Right? So there's no static ingest with MixApart. Everything happens on demand when the computation requires the data. So in this case, it's about 16% faster, MixApart. In the CPU-intensive case, MixApart is about 28% faster. This is because in the CPU-intensive case, the map tasks their I/O rates are lower, so the enterprise storage system can actually sustain the workload better. I mean, these results are expected, and just because of the overlap, so there's no magic here, right? So this is why we decided to focus our remaining sort of evaluation or remaining analysis on trying to understand the scalability estimates of a system such as MixApart. And the best way to do that is to start by having an ideal version of Hadoop, where there's no static ingest. The entire data required by MapReduce computations is in HDFS when the jobs are being submitted. So there's no static ingest from NFS into HDFS, right? So we're being fair to Hadoop to understand how MixApart compares against Hadoop, right? So we're trying to see how they sort of match. So again, with the MicroBenchmark, I'm showing here job durations for Hadoop ideal, so the version where there's no static ingest, and Hadoop plus ingest, the previous version. And the difference between the two lines is actually the static ingest time, right? The x-axis is the data reuse ratio, which is irrelevant for Hadoop, right? It's only relevant for MixApart. That's why you see the flat line there, the horizontal line. So with MixApart, as expected, the blue line, MixApart gets better as you get more reuse, right? So for instance, in this case, because it's able to utilize the cache more effectively when it gets higher reuse, in this case, when we have 0.6 reuse, MixApart is able to match Hadoop because it gets 60% of the traffic from the cache and 40% from the enterprise storage, essentially. So then we went and did some job mixes. So we have two jobs cost-scheduled, MixApart and Hadoop ideal. Job A has high priority and high reuse. Job B has low priority and low reuse. I'm showing on the y-axis the time normalized to Hadoop's time. And you can see in this case, the two jobs have similar durations, right? Now let's see why that's the case. So I'm plotting here the timeline for both Hadoop in red and MixApart in blue to see what happens behind the scenes. So with Hadoop, A computes first, takes the entire compute tier, and B waits, right? And then after A finishes, B computes. With MixApart, A computes because it has high reuse from the cache. It's able to utilize the cache effectively. And MixApart actually prefetches data for B while A is running, right? Because B has low reuse in this case. And then when A finishes, B is able to compute because all the data is in the cache. So this goes back to our MixApart in action example. The second use case is a bit more interesting, and it showcases the compute scheduler. So I have here again two jobs, and you can see the first job is longer, but the second job is slower. Again, high priority, low priority. The reuse is inversed. And again, I'm plotting the timeline to understand what happens. So with Hadoop, as before, compute A, B waits, compute B. With MixApart, the two jobs compute at the same time. Why? Because A, if you look carefully, has low reuse. So it's bottlenecked on the enterprise storage bandwidth. It cannot utilize the cache, even if it has high priority. So then there's idle compute slots. There's idle compute slots available, and MixApart's compute scheduler is work conserving that way. Right? So it's able to give those idle slots to the second job to B so that both jobs run at the same time. Right? So on average, we get the same numbers. We also did some experiments with Facebook traces. We got some traces from Yampe, from the Berkeley team, and we used their stream framework to replay these traces. We chose 3 hours from a large Facebook Hadoop trace with various reuse for replay. And I'm showing here the job durations in seconds on the y-axis for the 3 traces. right? And you can see again that MixApart matches the Hadoop version when ignoring ingest, the ideal version of Hadoop, right? I'm also showing compute concurrency here. It's a CDF, but the takeaway from this slide is that the map phase parallelism and the reduced phase parallelism curves are similar. So in summary, MixApart enables MapReduce style analytics for data that's stored in enterprise storage systems. In our case, the enterprise storage system is a single reliable data store, so we get optimized storage efficiency and simplified data management. We show that MixApart is faster than the regular traditional ingest and compute Hadoop, and comparable to Hadoop when we have no ingest, so the ideal version of Hadoop. So with that, I conclude my talk, and I'll be happy to take any questions.
Akshat Aranya, NEC Labs. You said that you get the I/O characteristics by running the job and figuring out how much throughput it would need from the system. How do you account for the fact that the storage might be the bottleneck? It's showing whatever it is asking for, but the storage might be the bottleneck in the map phase, which actually it typically is. So you could have done your job faster if you had fetched the data faster.
So that's a good point, right? So if the map phase is very I/O intensive, then indeed, I mean, there's not much you can do if you don't have a lot of reuse from the cache, right? You're going to be bottleneck on enterprise storage no matter what. Our studies show that workloads at Facebook, for instance, have jobs that are on the CPU intensive side on average, right? So you would expect a mix, but on average they're on the CPU intensive side, as in they're not as I/O intensive. Now, there's also efforts out there that try to scale out enterprise storage systems. So even NetApp is selling clustered ONTAP, for instance, which provides you much more bandwidth, right? So 10 gigabits, even more, right? So with that, you can sustain much larger compute clusters, even if the jobs are intensive. No. But the current evaluation indeed shows is more applicable for CPU intensive jobs.
That is fine, but like using the idea of saying that my job is using so much I/O resources, therefore that's the rate I will prefetch at.
Yeah.
Suffers from the problem that the I/O might have been bottlenecked, and then you're shipping stuff slowly because that's what you saw happen earlier.
The I/O to enterprise storage, right?
Yeah.
That could happen, right? So we have the notion of what's the available storage bandwidth. In our current design, we actually we claim we're bottlenecked on network. And we allocate, for instance, if your enterprise storage gives you 10 gigabits per second, has a 10 gigabit per second link, we allocate only 10% of that link to analytics, like 1 gigabits per second. Fair enough. The other point is these MapReduce workloads, I mean, they do a lot of streaming, so you could expect a lot of sequential I/O with some smart scheduling behind the scenes.
Okay, thank you.
Fabian, BRS, EMC. I was wondering, this filers or the storage, enterprise storage systems, they're actually using critical applications that usually, it's very common them to max out the bandwidth of your storage system if you're running a database on that system. So have you thought of the use case for this?
So we did some experiments on understanding the performance isolation for when running analytics and critical enterprise workloads on the same shared storage system, right? Because actually even in the title, we're claiming to do this on shared storage systems, right? Yeah. I mean, quanta scheduling has been shown to provide good I/O isolation. And in this example, for instance, in this experiment, I'm showing IOPS. So I'm showing the performance in IOPS when I'm mixing enterprise and analytics. And for enterprise workloads, I'm using two I/O intensive one, MicroBenchmarks, the random one and the sequential one. And I picked the I/O intensive trace from the MSR traces. And I ran that trace in the default way, so the actual trace. And then because that trace didn't really prove to be I/O intensive at all, so if you look at the graph, it's not actually impacted. So in this experiment, we allocated 10% of the bandwidth to analytics, 90% to enterprise. And what you see from the two first sort of bars, that's the normal thing, right? So if enterprise is I/O intensive, you should expect 90% performance out of the total of 100, right? But the third bar actually shows that with a real trace, enterprise is not impacted because it's not as I/O intensive. So what we then did was we increased the speed of the trace, right? So we made it go faster. And just to show the isolation, right? So even with 10x speed up, you can see the isolation of the two workloads.
Thank you.
Yeah.
All right. Oh, there we go. Thanks. Joe Buck, UC Santa Cruz. So there was a a survey out of Carnegie Mellon in December 2009 that looked at some traces from Yahoo. And it suggested that more than 99% of data that they processed via Hadoop was processed within the first hour that it exists on the cluster. Did you happen, in looking at the surveys you cited, did they delve into that aspect of their traces at all?
Did we delve into that aspect?
Did you notice them mentioning that? Because if that holds for your system, it would seem that you could just stream data right into your cache, and then it's hot. And then your ideal Hadoop is the normal case for more than 99% of the queries.
So that's a great point. We noticed that aspect. The current design is a bit more generic, but you could always plug in better prefetching policies or better sort of cache warm-up policies, and according to the workloads. And indeed, that's a great case, the 1 hour thing and populating the cache with that. Yes, I agree.
Okay, thank you.
Yeah.
Let's thank our speaker again.